we have the last model, MMS model. So what is MMS again? Markov arrival, Markov distribution, but S can be any number. In our case, in this topic particularly, we consider S equals 2, 3, 4, like this. So for this MMS model, still we have a formula. So here we look at the table, same matrices can be calculated, but there are a few differences. Since mu is service rate for one server, now when you look at the server utilization, we have to divide lambda by not just the mu, but number of servers and the service rate. So remember this. And the average number of units waiting in queue, it says that you have to see the following table. So let's hold it, but I will show you how to use a specific table to find this average number of units waiting in queue. That is NL, right? If you get NL, then next, what is number of customers in system? Actually, it is the same. Number of customers in system is the sum of number of customers in line plus current numbers in service. So let me repeat just one more time. Waiting line, there are number of customers waiting NL plus service. In the service area, this is a work in process, right? So work in process for customers. Therefore, work in process is arrival rate through time, right? So in this area, particularly, arrival rate is not lambda. But what is the throughput time? Service time is the throughput time. So 1 over mu. So we can simply add lambda over mu to get NS. So as far as we have this NL, we can easily get NS with lambda and mu. Okay, average time that units spend in queue is TL, and it says that NL over lambda is the formula. So again, TL, we have NL over lambda. So therefore, if you have NL, you can get TL. But interestingly, if you look at this formula more carefully, you can also find Little's law in this case as well. For the service area, we use the Little's law in this way, right? So arrival rate, throughput time, and throughput time is 1 over mu. How about waiting? In this waiting area, similarly, what we can do? Let me just rewrite this Little's law. Little's law in this area is working process is customers in waiting line equals to arrival rate. Arrival rate is still lambda. And multiply throughput time. What is the throughput time for just waiting? That is TL, right? So therefore, from here, if you want to know TL, what you can do? You just divide NL by lambda. So move lambda and you will get this formula. So although it does not say work in process, but NL is work in process. Therefore, to get the throughput time in the waiting line, you can see that you can simply divide the NL work in process by the arrival rate. So now you may see Little's law is really powerful, not only in the process analysis, but also it can be used in queuing system analysis as well. Excuse me. Okay, the last one is TS. So what is TS? Time in the system. So time in the system is, let me erase this a little bit. Again, queuing system is two parts, has two parts, right? So we can get this waiting time and service time. So time in the system equals to time for waiting, TL, plus what is service time? 1 over mu. Okay, now only one thing left. What's left? How to get? Yes, NL. Because it says that we have to see the following table. So what is the table? What we need to use here in the following table, it says that lambda over mu is given in this column. And in this row, the first row, what we have is number of servers. So it is S. So given S and given this lambda over mu, what we can find one value in this table. So as an example, suppose we have lambda over mu given as 2.4. If you have lambda and mu, you can easily divide it, right? And let's say we have 7 servers. Then how can we get this number, NL, number of customers in line? You will look at the ratio here and you will find 2.4 where? Here. And then in this row, you are trying to find the case when server is not 1, not 2, not 3, not 4, not 5, not 5, but there is a 7. So with this 7 and this particular row, we have this value that is 0.0065, and that's NL. Okay, so let's just solve the problem, the example 3.2. So there is a drive-up window at a fast food restaurant. Customers arrive at the rate of 24 per hour. So what is the lambda? Lambda is 24 customers per hour, and the arriving is Markov. There is a drive-up window, and the employee can serve one customer every 2 minutes. So if you convert in hourly rate, since every 2 minutes there is one customer, you can easily figure out there are 30 customers you can serve. It says that Poisson arrival and the exponential service rate, so MM. And we assume that there is one more identical trained server. So currently we have one. So it was previously MM1 model. Now we have one more server, so MM2 model. So what is this number? S equals to 2. Okay, so given this information, what we want to know? We want to know average number of cars in the system. So we want to know NS and the total time customers wait before being served. So that is not TS, but it is TL because time in the waiting line. So let's try to solve this NS and the TL. So to get NS, if you look at the formula here, first what you have to get, NL. And then you need lambda over mu. Again, using Little's law, you can easily figure out this is a number of customers in service. So if I rewrite one more time here, NS first equals to NL, number of customers in the waiting line, plus number of customers being served. Then this part is based on the Little's law. Although formula is given, we can see that arrival rate multiplied by what's the throughput time for the service? It is a service time. So we can rewrite NL plus lambda over mu. We know lambda and mu already here, but we don't know NL. So what we have to do, since this is MM2 model, we cannot use MM1 table, but we have to use a special table. So let's try to use the table. To use the table, there are two parameters we use. The first one is lambda over mu. So what is the lambda over mu? Lambda is 24 over 30. So the ratio is 0.8. Okay. Now, what is S? S is 2. So given these two parameters, let's see how to find an L. What's given? The first one is lambda over mu, and in our case, 0.8. What is S? S equals to 2. So let's look at lambda over mu column first, and let's choose 0.8 here. And the number of customer and number of servers are 2, so we want to focus on this 2. So what is the value? The value that you are looking for is this. So the answer NL for this question is 0.1523. Okay, so let's go back here. So now we got NL. NL equals to 0.1523. And here it says that number of customers in the system is this NL 0.1523 plus lambda over mu here given, and we already calculated this as a zero point 0.8, so 0.8. So what is the total number of customers in this system? That is 0.9523. Okay, now second question. So what is the time in the waiting line? So TL. Yes, the formula is given, so you can go back to the formula. But again, I want to emphasize the powerful leader's role. So what is the leader's role in this case? In the waiting line, we have NL, that's number of customers. To get this, what is the arrival rate? Lambda. What is the throughput time for just waiting? It is a TL. So from here, to get TL, what do you need? NL must be divided by lambda. That's it. So we can use this TL equals to, what is NL? NL is already given as 0.1523, and it should be divided by, what is the lambda? Lambda is given as 24. But this is hourly based rate, so it is answer is based on hour, and you can get it is 0.06 hour.